everybody. We are going to start dynamics. So dynamics is the fancy physics word for forces. That's some alliteration for you. Love alliteration. Okay, so we're going to start with inertia. We can see this nice gentleman or gentlewoman who's crashed their motorbike into these tires and is flying off of the bike. So think about why somebody that would happen to somebody if they're crashing into something. Why would their body keep flying? Why does that happen? What's going on? The reason why is inertia, and so we're going to talk about that today. So inertia is the tendency of an object to remain at a constant velocity. The law of inertia is Newton's first law. And Newton's first law states that an object in motion will stay in motion, and an object at rest will stay at rest unless an outside force is applied to the object. So basically, if there is no push or pull, there's no force, no push or pull on an object, then it will stay at a constant velocity. So no forces means no acceleration, which means constant velocity. So I've got this little beetle here. I'm not going anywhere unless someone forces me to. I'll keep going until something stops me. So think of inertia as kind of stubbornness, okay? It's the stubbornness of mass. It doesn't want to change what it's doing. It wants to keep doing what it's been doing. And the only thing that's going to make it change is a force, or a push or a pull. So force is any push or pull. And the units for force are newtons. We use a capital N for newtons. So no lowercase n's. I want to see you use capital N's for your units. And our really big, super duper important equation that we're going to be using almost all year, applied in different situations, is F equals ma, or F ma, where F is force, m is mass, and a is acceleration. And the units come from this. So if you look at mass times acceleration, mass is in kilograms, and acceleration is meters per second squared. So a unit of force is a kilogram meter per second squared, which we call a newton, just to make things easier, so you don't have to write so much stuff. We tend to call motion with forces by the term dynamics, because the objects are being affected by outside influences. They're very dynamic. They're not static. They're dynamic. They're moving. They're changing. Okay? Dynamics gives us the mechanism or the cause behind the motion. It gives us the reason why things accelerate and decelerate. So we have four fundamental forces. It's the gravitational force, the electromagnetic force, the strong nuclear force, and the weak nuclear force. These four forces govern everything in our universe and how things move and interact with each other. This class is only going to be dealing with the gravitational force and a little bit with the electromagnetic force. If you are taking some more advanced physics courses in college, then you'll learn about the strong nuclear and the weak nuclear force. But I'll give you a brief overview of each. So gravitational force has to do with masses interacting. The electromagnetic force has to do with things like electrons and protons, things that deal with electricity and magnetism, light. Light is EM radiation. The strong nuclear force and the weak nuclear force, these deal with interactions between particles in atoms and interactions between the particles that hold those particles together or make up those particles. So this is particle physics stuff. This is more small scale stuff, dealing with things like quarks and how the nucleus of an atom stays together. And so those are for more advanced classes or just different topics. So the gravitational force is the force due to gravity says that any two objects will feel a force of attraction, which depends on their masses and distances apart. Okay, so this force due to gravity is due to mass and how far apart things are. The mass is given in kilograms, and this is the amount of matter or stuff inside of an object. And weight is given in newtons. This is the amount of gravitational force felt by an object. Common rookie mistake that I really, really, really don't want to see you guys make. A lot of people mix up mass and weight, and that's because of how we do things over here in the US. We say, how much do you weigh? And we say, 160 pounds. Well, how much do you weigh should really mean gravitational force, but the way that we use it here, we get it mixed up with mass. It's kind of a murky ground. And pounds can be used for mass and weight, but they're a different kind of pounds. And so it's kind of weird how we do things over here. So it's easy to get them confused. Okay. How much do you weigh is the amount of gravitational force felt by you. How massive you are is the amount of stuff that's inside of you. So think about mass and weight. Do you think either of these values change when you go somewhere else, like say to another planet or into space? Does your mass change? Does your weight change? Do they both change? Think about that for a minute. So mass is the amount of stuff in an object. So if I were to suddenly transport you from Earth to the moon, I'm not changing the amount of matter or stuff in you. So the mass shouldn't change. So mass is kind of universal. It's going to stay the same no matter where the object is located in relation to another object. Weight, on the other hand, is definitely going to change. The gravitational force here on Earth is different than it is on the moon. So your weight will be different between the Earth and the moon, but your mass will stay the same. So the formula for the force of gravity is Fg is equal to mg, where Fg is the force due to gravity, m is your mass, and little g is the acceleration due to gravity in meters per second squared. You could also just write this as a sub g, so that you know it's the acceleration due to gravity, or just a. So again, big rookie mistake. Mass and weight are not the same thing. Mass will stay constant regardless of location. It's measured in kilograms. Weight changes depending on your location with respect to other masses, and it is measured in newtons. So, little g, your acceleration due to gravity, varies depending on the side of the planet and the distance to the object. For example, on Earth at sea level, g is equal to 9.8 meters per second squared. And that's the value you've been using for freefall acceleration. On the moon's surface, little g is equal to 1.6 meters per second squared. On Jupiter, g is equal to 24.5 meters per second squared. So really big acceleration due to gravity, whereas the moon is much smaller compared to Earth's. And on the sun, g is equal to 274 meters per second squared. And this is measured from if you were standing on the photosphere, as the visible part of the sun. So again, your weight is going to stay the same, or your mass is going to stay the same. See, even I do it. Your mass is going to stay the same no matter where you are, but your weight is going to change depending on where you are in relation to other stuff. Earth, moon, Jupiter, sun, you're going to have very different weights. So I'd like you to try this example for fun. Determine your weight in newtons on Earth, the moon, and Jupiter. And we're going to say that 1 pound is equal to 0.45 kilograms. So you should be able to convert your weight into kilograms, your mass, but your English weight, you should be able to convert your mass into kilograms. And then you should be able to use those accelerations due to gravity on the other planets to find your weight in newtons. All right, that's all I've got for you. Check out my inertia example video. That will be coming up soon, and that will help you out with the upcoming example demonstration that you are doing for me.